for this problem. So now let us move on to some examples that are a little bit more elaborate than the standard case. And the one example I'd like to look at is the non-uniform elements. Let us assume that we're looking at an axial problem involving a non-prismatic rod, such that the area of the cross section varies linearly with respect to the axial coordinate, given with some formula. For example, the formula shown on the right-hand side, upper right-hand corner of the slide. A sub x is equal to a1 times 1 minus r times x over L. And if you evaluate this formula at x over L, x equals to 0, you end up with a1, regardless of the value of r. And if you evaluate this formula at x equals L, you end up with a1 times 1 minus r as the area on the right-hand side. So we can then use r as a variable, an input parameter, a geometry parameter that controls how much this variation is from one end to the other. When r is equal to 0, we're obviously looking at a prismatic beam. And when r is equal to 1, precisely, we're looking at a beam with a sharp end. And of course, that particular case where r is precisely equal to 1 is not going to be a solvable problem. So we would then restrict r to lie between 0. It could be equal to 0, but it cannot be greater or equal to 1. It should be less than 1 strictly. So with those caveats, we can just carry out the principle of virtual displacements and see what we get. So in this particular case, our stiffness matrix is almost identical, except our now constitutive relationship has this variation of A embedded in it, and we need to take care of that variation in our integration. When you do the integral properly, you end up with this stiffness matrix, which looks almost the same as the normal prismatic stiffness matrix, well, with this r in place. And as you can see, if r is equal to 0, you recover the original prismatic stiffness matrix. And when r is equal to other values between 0 and strictly less than 1, the stiffness matrix will be different. Now we can go about obtaining an analytical solution for this problem. Let's see what we get. So here is the governing equation, the second order ODE. And now I have taken care of the fact that A is a variable, so I did not really carry out that outermost derivative, and I left it alone. So now if I integrate this equation one time on both sides, I'll end up with a constant on the right-hand side, which I will divide by EA and integrate once more to get the analytical solution. So through this integration, I will have generated two integration constants, C1 and C2, and I can set their values based on the nodal displacements at nodes 1 and 2. If I evaluate U that I have obtained, the exact solution that I've obtained at x equals 0, I'll end up with this relationship. If I evaluate the same at x equals L, I will end up with the other. And then I can express those integration constants as a function of the nodal degrees of freedom by inverting these two relationships in terms of C1 and C2. And after I plug in the C1 and C2 into the original analytical solution, after some rearrangement, I will have ended up with these shape functions. So now the shape functions that are exact for this problem are not linear polynomials. They're not polynomials themselves even. They are just some composite functions of logarithms, logarithms of polynomials, if you will. And n1 is that, n2 is that. So if you wanted to obtain an exact solution for this particular problem, then you would have to use n1, this n1 and this n2, rather than the one we have computed before using the principle of virtual displacements in a slide earlier, a couple of slides earlier. If we use these exact shape functions in the principle of virtual displacements, this is the stiffness matrix we would have obtained. And now we can compare that to the one that we had constructed using linear shape functions. And let's just pick a generic value of r equals a half, a legitimate value, that renders this indeed a non-prismatic element. So the exact one that we have obtained using the exact shape functions will look like this, 0.72 EA1 over L times this matrix. And the one that we have obtained with the linear albeit approximate shape functions, would be 0.75 EA1 over L. And as you can see, the use of the linear shape functions will only give us an approximation, and the nodal displacements that we would have computed by solving the discrete equilibrium equations would only be approximate but not exact. And with this example, I'd like to point out the fact that not every problem, for a given problem, we will not always be able to obtain an exact analytical representation of the shape functions, the correct shape functions, like we did for this particular problem, which was possible. And in that case, we will have to resort to lower order polynomials to approximate the displacements. And hopefully, our approximations, like in this problem, are not too far off from the exact values. 0.75 is not too different from 0.72. And of course, if the length of the member is shorter and shorter, I think this approximation will become better and better. So what is the source of this discrepancy? Again, let's elaborate a little bit more on that. Recall that by using the linear shape functions, we assumed the displacement field varied linearly. Does this satisfy our ordinary differential equation? For this problem, it does not, as we obviously know, because if you plug in this displacement field into the ODE that we have at hand and just carry out the little algebra, you'll end up with E times A sub 1 times R squared over L squared times U1 minus U2. Well, is this equal to 0 for all x's? Hardly. Of course, there's an exception. Well, there are a couple of exceptions. One of them is trivial. The one that is trivial is the rigid body motion. Of course, if you have a rigid body motion, you will have satisfied it, but that's a trivial, useless result. And the other one is when R is equal to 0, which is the case when you have a prismatic beam, for which indeed the displacement field would be varying linearly. Okay. So let us now move on to the application of the principle of virtual displacements and work to determine equivalent nodal loads. Because so far we have only looked at nodes that are applied at the ends of our members. What if we have distributed loads, or we have loads applied at the interior of an element, like the middle of an element? What do we do? Let us begin the determination of equivalent nodal loads for a planar beam under flexure and axial loads under distributed loads. So we have our nodal quantities, fine, but now in this problem I'd like to consider the possibility of having a P of x and a Q of x, which represent the axial distributed loads and the transverse distributed loads. So let us pack these two quantities that could be specified by the user into a vector and have our Q of x represent the little p of x and the little q of x for this problem. So recall that we have our real displacement field for this problem, and that it was interpolated using the shape functions of our choice. Hopefully they're good shape functions or exact shape functions for the problem at hand, which may not always be possible, but we will have shape functions. And for this axial flexure problem, our shape function matrix is going to be 2 by 6 for the particular given arrangement of the vector of nodal displacement degrees of freedom, or kinematic degrees of freedom, where NA1 and NA2 are the axial shape functions, and the 4 N sub Fi are the flexural shape functions. And we can choose, as we always choose, the same shape functions to interpolate the virtual counterparts of the displacement degrees of displacement fields, and then use the same shape functions here. So del u is equal to n times del delta. Now, to consider these distributed loads in our principle of virtual work scheme, principle of virtual displacement scheme, we need to really compute their contributions to the external virtual work, because that's all the contribution that they will make into that statement. They will contribute only to the external virtual work, and they'll contribute in a quite simple manner. All we need to do is just take the inner product of the del u vector with the q vector that we have just defined and integrate that quantity over the entire length of our member. So that is just going to give us the entire virtual work contribution of these distributed loads, whatever their variations are along the length of the member. So q in general could be a function of x. So I rewrote that inner product as follows. It's del U transpose times Q. And then I can substitute in the representation of my virtual displacement field with respect to the shape functions and the virtual nodal kinematic degrees of freedom del delta. So I have del delta transpose and transpose multiplying Q. And since del delta transpose is not a spatially varying quantity, I can pull it outside the integral. And then I can relabel the integral I have as F equivalent distributed loads. And this is precisely it. If you compute this vector of equivalent distributed nodal loads and take its dot product with the virtual nodal kinematic degrees of freedom, you will have obtained the contribution of these distributed quantities to the external virtual work. It's simple as that. So with this, we have defined F equivalent distributed as the integral of Q convoluted with the shape functions. So please take a note of the fact that if you change your shape functions, the equivalent distributed nodal loads will be different. If you can use the exact shape functions for the problem at hand, the equivalent distributed nodal loads will be exact. If you use approximate shape functions for the problem at hand, this equivalent nodal distributed loads will contain errors, just like the stiffness matrix will have contained errors. So let us apply this formula we have just obtained for a simple case of constant axial load and constant transverse load. Plug the results back in. So the first big matrix, which is 6 by 4, is the transpose of the shape function matrix for the problem at hand. And we multiply that with a 2 by 1 vector of P and Q, in which case it's just P naught and Q naught, two constants. If you then carry out the integrals, you obtain these quantities. So the equivalent distributed nodal load for a beam that is loaded with a constant axial load and a constant transverse load as follows. And these quantities should be no surprise to you because they're exact for the problem at hand, and that is simply because we're dealing with the correct shape functions for this problem. What happens if we have concentrated loads on the other hand? Let's say that we have a concentrated transverse load of magnitude Py located somewhere and a Px located at the same spot, say x sub c, from the left node of the element. Let's just pack these two quantities, the axial load and the axial transverse force, into P. And I could have also included a concentrated moment at the same location. Please try and carry out that exercise on your own. It's not different from the procedure that I will show you for this particular case. But if I have concentrated axial force and transverse force, then the principle of virtual work contribution from those would simply be the value of the virtual displacement field at x sub c, the location of application of these external agents, dot producted with their values, p. So now the displacement vector is simply u evaluated at x sub c and v evaluated at x sub c. So there's no integral involved in this case. All I need to do is just really go ahead and evaluate the shape functions at those locations. Because del u is simply del delta times n transpose. And if I evaluate n transpose at x sub c and multiply with that p, I will have obtained the concentrated equivalent nodal loads. And of course, for the planar beam, the procedure is simple, right? That's what we would have for the concentrated equivalent nodal loads applied simultaneously. Axial and transverse loads applied simultaneously at location x sub c, and you can just carry out that vector product, vector matrix product, to obtain a 6 by 1 equivalent nodal load vector from this application. So this was quite simple and straightforward. Another problem that I'd like to talk about in the context of principle of virtual displacements is the inclusion of the effects of, say, initial strains. Initial strains can be in our problem due to pre-stressing or thermal loads. Let's just go back to the constitutive law, for example, for the axial problem, and just discuss this consideration of axial initial strains in the context of an axial problem only. But of course, you know that this discussion can be generalized for other problems, the torsion problems, the flexural problems as well. What happens if you have, say, an initial curvature? You can consider those kinds of problems in the same manner that we're considering here for the axial problem. For the axial problem, however, our total strain comprises two parts. One part is the mechanical part that is given to us through the constituent relationship, that is sigma divided by Young's modulus. And another part, the initial strain part, that could be coming, say, from thermal strains. And I denoted that as epsilon sub x superscript 0. So I can kind of rewrite this expression and obtain sigma in terms of the total strain and the initial strain. And it's just simply Young's modulus multiplied by their difference, really. And for the general case, I can think of this relationship as the subtraction of two vectors, which are c times e and c times e naught. Right? That's just a generalization of the uniaxial formula, scalar formula that I put up top. The contribution to the internal virtual work then is simply the virtual strain field dotted with the stress field, and that scalar integrated over the entire volume of your element or structure. And if I plug in the constituent relationship I have above, this is what I will get, this integral. And I'll split that integral into two parts. And the integral on the left, therefore, is the standard one. This is the standard relationship we would have for just a purely mechanical problem with no initial strains. And another part that comes from the initial strains, that's the term in the red boxes due to the initial strain contribution. So let us just bypass the standard term and take a look at the initial strain contribution in isolation. So this is what I had, a virtual strain dotted with c times e naught. And here e naught needs to be well defined given depending on the problem. And I will define it in the context of a thermally induced initial strain. And recall that our strain displacement relationships would relate these quantities to the nodal quantities, whether virtual or real. So the one I will use here is the virtual one. I'll just plug that in and rewrite the del epsilon transpose as del delta transpose times B transpose, and move the del delta transpose outside and end up with this integral that I need to carry. And then this integral, if I carried it well, will be a properly sized vector of equivalent nodal loads due to this initial strain. And that should be computed from the context of whatever the problem is, and it's just an integral that we need to carry out. So let's, as I was telling you, let's just specialize this relationship for uniaxial thermal loading on a planar beam or rod. We will have the axial strain, or rather this strain quantity, the resultant initial strain quantity comprising two general parts, an initial axial strain and an initial curvature. And as I was telling you, I'm just going to omit any initial curvature, but only include axial strain that is thermally induced. And if that's the case, epsilon sub x superscript 0 will be just the thermal expansion coefficient times the change in temperature, delta T, whatever it is, and plug that result into here. And our B matrix is defined by whatever shape functions we have and their appropriate derivatives. And then C times E naught is simply that. So we're essentially multiplying our B transpose matrix with this 2x1 vector whose second component is simply 0 and whose first component is the axial stiffness, EA, times alpha times delta T. And if you carry out the integrals and do the necessary simplifications, because there are many zeros, multiplying all the second derivatives of the flexural shape functions will all be multiplied and go away. Only the axial components will come in, and the result will be quite simple. We will just get axial equivalent nodal loads at degrees of freedom locations 1 and 4, which is where our axial degrees of freedom were located in this particular ordering. and those loads will be simply equal to each other in opposite directions, and their magnitudes will be EA times alpha delta T. So if you are given, for example, a truss under some thermal loading and no other mechanical loading, you will still obtain internal stressing and reaction forces if the truss is indeterminate, whether internally or externally indeterminate, due to these equivalent nodal loads that you can see they're computed in a quite simple manner. And if you have combinations of these effects going on for your given problem, your equivalent nodal loads would be just a simple sum of all these different effects. If you have concentrated elements, they'll contribute to the concentrated equivalent nodal loads. If you have distributed elements, using the appropriate integration, you can include their contributions to the equivalent distributed nodal load vector. If you have some initial strains, whether it's from thermal problems or geometric imperfections, you can include them in here. And of course, those integrals are all dependent upon shape functions, and in the particular case of initial strains, constitutive properties C as well. So that concludes our discussion of the principle of virtual displacements and its application to frame problems at hand. We have discussed the shape functions, how they are rearranged to have their generalized coordinates represent physical quantities like nodal displacements and rotations. We have used shape functions and exercised them through the principle of virtual displacements to obtain the element stiffness matrix. We have exercised that same principle to obtain the element stiffness matrix, for example, for non-uniform members. We've also discussed the equivalent nodal loads using the principle of virtual displacements. We've considered distributed loads, concentrated loads between nodal points, as well as thermally induced initial strains. And this concludes our lecture on the principle of virtual displacements.